ponoć mieszka w Warszawie, a jest profesorem na Uniwersytecie Wrocławskim. Mogę tylko powiedzieć, że na normalnym amerykańskim uniwersytecie taka możliwość istniała, ponieważ profesor jest po to, żeby był na uniwersytecie, a nie po to, żeby był. Ale to jest Europa i pamiętam, że również we Francji
no, we Francji
mieszkało się
wszyscy mieszkają w Paryżu, niezależnie od tego, czy są w Lille, czy w Marsylii,
czy Dijon, czy mój przyjaciel szlatowy, czy
Marek Abramovicz z Triestu do Katanii latał. Przez 2 lata.
Także to jest takie europejski zwyczaj, ale w Ameryce studenci płacą na ogół, domagają się, żeby profesor na każdej krzyczeć. Prosimy pana.
Dziękuję.
Ja chciałem zwrócić uwagę, panie profesorze, że w Polsce studenci też płacą.
Ale nie są wymagające. Płacą za to, co dostają. Dziękuję bardzo za zaproszenie. Moje zadanie się troszeczkę bardziej skomplikowało, ponieważ teraz muszę moje notatki tłumaczyć na polski, ale mam nadzieję, że sobie... Nie, notatki zostały. W każdym razie to, co jest w notatkach, będę musiał tłumaczyć na polski, mam nadzieję, że sobie dam radę. No
chyba, że pan ma notatki.
Nie, mam notatki po angielsku, ale podejmę to wyzwanie. A tytuł mojego wystąpienia jest Grawitacja. Obawiam się, że ten kabel jest po prostu, musi być.
Tak. Punkt zaczepienia dało się przesunąć.
Ale punktu zaczepienia nie da się przesunąć, ponieważ ta kamera musi obejmować. Dobrze, postaram się tutaj nie spowodować jakiegoś... Ja rozumiem.
Pan jest ubezpieczony przed złamaniem nogi na terenie Centrum Fizyki Teoretycznej?
W zasadzie tak, to znaczy jeżeli bym złamał nogę w czasie wykonywania obowiązków służbowych, to mój pracodawca... W gipsie, tak, ale mój pracodawca, rozumiem, będzie zobowiązany do wynagrodzenia mi. A nie, a rzeczywiście jestem ubezpieczony. Tak sobie właśnie przypomniałem. Okej. Grawitacja jako źródło deformacji. Jeśli czas pozwoli, ja będę w zasadzie zajmował się teorią klasyczną, ale jak czas pozwoli pod koniec, powiem chwilę na temat odpowiedniej teorii kwantowej. Ponieważ pan profesor Biura uświadomił mi, czy poprosił mnie, żebym był w miarę możliwie, ten wykład był możliwie najprostszy, ponieważ tutaj są...
My się bardzo do tego postulatu przyłączamy.
Super, więc ja postaram się to zrobić w sposób możliwie prosty, ale w związku z tym ja nie będę tutaj mówił o ogólnej teorii, tylko opowiem o pewnym konkretnym przykładzie, a potem po tym przykładzie powiem, jakie są możliwe uogólnienia i w jakich kierunkach te uogólnienia zostały uczynione. Chciałbym może na początek wyjaśnić, co ja rozumiem przez słowo deformacja. Otóż ja nie potrafię tak z rękawa nie potrafię wypowiedzieć jakiejś takiej prostej definicji, natomiast chodzi mi o coś takiego, o sytuację podobną do przejścia od kinematyki czy mechaniki nierelatywistycznej do mechaniki relatywistycznej. Znaczy, w mechanice nierelatywistycznej wszystkie prędkości są dozwolone. Ja mówię, nie chciałbym tutaj być, absolutnie nie jestem precyzyjny, ale z grubsza chodzi mi o obraz. W mechanice nierelatywistycznej mamy dowolne prędkości, mamy zasadę względności Galileusza, prawda? No wiadomo. Przejście do mechaniki nierelatywistycznej związane jest w zasadzie z wprowadzeniem postulatu, też bardzo z grubsza, że istnieje pewna niezmiennicza skala prędkości. No? ta skalą prędkości, czy odwrotna skala prędkości, istnieje coś takiego jak 1 nad c, co do której pewna klasa obserwatorów się zgadza. Tam mamy jakąś tam wyróżnioną klasę obserwatorów i oni się wszyscy zgadzają, że wartość tego obiektu jest taka sama. Też z grubsza, oczywiście to wszystko jest znacznie bardziej skomplikowane, subtelne, jeżeli się zaczyna w to głębiej wchodzić. Na dodatek istnieje coś takiego jak zasada komplementarności, która mi mówi, że kiedy ta skala zmierza do zera, czyli to też nie jest takie proste, bo musimy powiedzieć, co to znaczy, że 1 nad c jest małe. No, możemy to sobie precyzyjnie powiedzieć, ale z grubsza znowuż, jeżeli ta skala zmierza do zera, to przechodzimy z powrotem do mechaniki nierelatywistycznej. I w związku z tym to, co ja będę nazywał deformacją, czy będę rozumiał jako teorię zdeformowaną, to będę w tym rozumiał w takim samym sensie, w jakim sensie przejście z teorii nierelatywistycznej do teorii relatywistycznej jest pewną deformacją. I tak naprawdę można to bardzo formalnie i porządnie zdefiniować, ale idea jest generalnie prosta.
To samo przy przejściu od klasycznej do kwantowej.
Przy przejściu do klasycznej do kwantowej sytuacja jest... Chciałem podać ten przykład, ale sobie pomyślałem, że pan profesor natychmiast mnie skontruje i powie, że to przejście oczywiście z klasycznej do kwantowej jest pewną deformacją i też bardzo dobrze określonym matematycznym sensie.
Mało rozwinięte umysł, dlaczego to się nazywa deformacją? Co się zdeformowało?
O tym to ja powiem. To o tym konkretnie powiem. Na przykład przestrzeń prędkości, prawda? Przestrzeń prędkości w szczególnej teorii względności ma inną charakterystykę niż przestrzeń prędkości w nierelatywistycznej teorii.
Wszystko, co ma inną charakterystykę, to się nazywa zdeformowane.
Deformacja jest...
Ludzie wymyślili to jest...
Prędkości relatywistycznej stanowią przestrzeń wektorową, prawda? Można prędkości...
No nie, no trójprędkości akurat spełnia, no nie do końca, prawda? To jest bardziej skomplikowana rozmowa. Trójprędkości są...
Logicznie ja bym raczej myślał, że teoria względności jest reformacją.
Dobrze, nie czepiajmy się słów.
Nazwa pochodzi od matematycznie...
Z dobrze zdefiniowanych obiektów. I można...
To ja muszę nie rozumieć. Dobrze, dziękuję.
Znaczy tutaj nie ma... Tutaj jak...
Nie, absolutnie. To jest najlepsze. Bardzo proszę o tego rodzaju uwagi, ja wtedy się czuję dobrze, wiesz, bo jest docenione.
Rzucasz go. Dzięki grawitacji on zostanie zdeformowany.
Niekoniecznie, na przykład sernik. No dobrze, sernik jak się robi, żeby nie było zapalnięcia. Jak zostawić to się zdeformować.
Dobrze, no więc ja może zakończę tą dyskusję po prostu mówiąc, że jest to...
Excuse me,
Yes.
we have to switch into English.
Oh, okay, good. Okay, thank you. All right. So the first thing I was trying to explain was Okay, well, I need to translate the title back. It's gravity as a source of deformation, and perhaps I will have a little bit time to explain why I put quantum in parentheses here. I was trying to explain what deformation is, and basically. The picture is that the deformation I understand in the sense in which the transition from non-relativistic kinematics or dynamics to relativistic dynamics is the deformation of the former caused by the presence of special physical scale or scale which is 1/c. And then I can deform the classical mechanics to get the relativistic mechanics by switching non-zero value of this, and I can turn back by actually taking a limit in which 1/c is actually 0. And similarly, I can do the deformation of classical mechanics to quantum mechanics, although there the situation is, I think it's a little bit more tricky because the semi-classical limit of quantum mechanics and quantum field theory is notoriously full of problems and subtle issues. So but this is still another example in the sense that I introduce another physical constant scale h bar, and then there is a well-defined mathematical procedure which actually tells you how to move or turn from classical mechanics to deform classical mechanics, which is a quantum mechanics. All right. So concrete, to be more concrete, because as I said, I wanted to be, I was urged to try to be simple and down to earth as possible. So I would like to consider an example of the particular deformation caused by gravity and the particular model of gravity. And then I will tell you, I will discuss it in details. And after that, I will tell you what are the generalizations. Okay, so suppose I am in flat space, and I have a standard relativistic particle with a Lagrangian, which is what? P mu q dot mu minus n p squared minus m squared. This is a standard Lagrangian for relativistic particle. I believe that everybody knows it. Essentially, it tells you that there are 4 positions and 4 momenta which form the canonical pair in phase space. So they form a standard phase space, which is a well, all right, standard phase space. Apart from that, there is a constraint which is imposed by this Lagrange multiplier n, which essentially which tells you that the particle, because it's a classical particle, it must be on mass shell. Okay, so this is essentially everything that there is in this action. What the action describes? Well, it describes a motion or a particle in space-time. So if it's x, y, and t, essentially we have something like this. It's a straight line, right? If you look at the equation of motion following from this, you'll find that the solution is a straight line. Okay. This is simple. What else do? So this action has a remarkable property that this is quadratic. It's very simple, nice, and elegant. What else do we know about it? Well, we know also that that this object here indeed is a momentum, because if I consider multi-particle systems, so many free particles, then I can construct an object which is a total momentum, and this total momentum is conserved. Okay, so the total momentum is nothing but the sum over I. If I have many particles, it's just a linear sum of the components of the particle, which means that
For free particles, every.
that's true, but it means that, well, actually this is much stronger than that, because of course for a free particle it's just trivial, right? However, we know that if I have some local interaction, so I let this particle scatter, then if I compute in the distant past, when all particles are free, I compute this momentum, and then in distant future, thinking well in terms of S matrix, for example, in the distant future, where again these particles, I have collection of free particles. I know that this object at the beginning of the process, so before the process takes place and after the process takes place, again, well, it's the same.
Each particular for momentum is conserved, not only there is some.
Yeah, that's right. That's true. That's true. On shell. When equation, any combination of momenta, because the components of momenta are conserved, but it follows from the translation invariance, as we all know, that if I include some interaction process between particles, so the particles are free, but they have some local interaction, that can be very nicely modeled.
There is no relativistic interaction.
Well, there is if it's local, if it's point-like, of course it is. There is a nice relativistic theory of point-like, delta-like interactions, of course. So if you have, but this is everything that we have, right? If you think about the way we actually do the quantum field theory, we do exactly this way. I mean, I have some particles, and they have local interaction. This is what quantum field theory, perturbative quantum field theory really is. Exactly, but the fields are carried by quanta. So if I think about perturbative field theory, it's nothing but the collection of Feynman diagrams, right? Which is essentially nothing but, this is Polyakov's view on quantum field theory. Okay, anyway. Okay, so this object is conserved, that we know. Okay, now imagine that that I switch on gravity, then what's happening?
Gravity, how do you switch on gravity?
First you have to become a god.
I'm switching, okay, I am switching, no, the switching on gravity means
It's no problem.
basically that,
Newtonian gravity?
no, just as whatever, well, the full-scale general relativity. I can switch full-scale general relativity just by allowing gravitation. So this...
But as a given
No,
background
let me finish the sentence. The idea is the following. Now, here I have a flat Minkowski space on which this particle moves. Now, this particle, and this is an accurate picture of the system particle plus gravity if gravitation constant is actually 0. If gravitation constant is 0, there is no interaction with particle, does not create gravitational field.
Claim that gravitational constant is equal to 1.
Or whatever.
Exactly 1.
Well, exactly 1 is anything.
So you see it there,
The deformation of the matrix will
small.
introduce changes. You don't need the gravitational constant to be different from 0 to have influence of space-time curvature, for example, on the motion of the particles.
I'm not talking at this moment. I'm not talking. So imagine this. Okay. So let me return. I will make it precise in a moment. But let me imagine the following situation. So suppose now I started having with a particle moving in a flat space. Now suppose now that the particle is coupled to gravitational field, which means that the particle actually creates the gravitational field, right? But that can be done.
But at least classically, we don't know how the point-like particle creates gravitational field.
We do know.
No.
Yes, we do.
Point-like particle?
We do. At least, well, we do. Certainly, we do it in 2+1 gravity that I'm going to talk about.
Which gravity?
In 2+1 dimension. And actually, we also do know how to do it. We also do know how to do it in 3+1 dimension.
No, there are no point-like sources for gravity. In 4 dimensions, there are no point-like sources.
Okay, we'll talk about it. I claim we can do it.
The most point-like is Schwarzschild, which is not point-like.
Oh, this is no. Hold on. This is not completely. This is not fair. Right, because it concerns the back reaction on gravitational field on the source, so it's not fair.
No, but there is no solution of gravity.
Well, all right, okay, okay. This is. Could you please let me continue? Because now I'm trying to make to form a picture. And this picture will make sense in the context of the theory I will talk in a moment, okay? And then we'll try to generalize. Anyway, so imagine this situation, which is a situation in which the particle creates its gravitational field, but then, of course, we cannot avoid the question: what's happening? What is the back reaction of the gravitational field on the particle itself? And my question is. So the question I would like to address here is what's going to be the particle motion when the back reaction is taken into account? So I have a particle, it creates gravitational field. What happens if I consider the back reaction of the gravitational field on the particle itself? So what if I take the back reaction?
This is a very ambitious program because it has not been even solved in electromagnetism.
True. Let me finish. Let me make another. Just finish this. Of course, it was not solved for electromagnetism, but it can be solved in a particular situation in which I will be concerned, because after all, I am concerned. My point is to tell you about the deformation. So I claim that this problem can be solved in 2+1 gravity, in the context of 2+1 gravity. And I would like to tell you in detail, so because as I told you, I want to give you an example, so I will show you in details how to do it in the context of 2+1 gravity. And what is the result, and why this result is interesting. So let me actually tell you why it is very hard to do not impossible, in the context of physical 3+1 gravity. And the reason is pretty simple. So suppose I have this particle. The particle creates some gravitational field. But what do we know from Einstein equation? Well, the Einstein equations well, let me erase this one. What the Einstein equations are telling you, they tell you that actually the components of Ricci tensor are completely fixed by the material source. So if I know the material source, the Ricci tensor is known. Okay? But in 3+1 dimension, that it doesn't fix geometry for you, because R mu has 10 components, right? So Einstein equation fixed for you 10 components, 10 independent 10 components of Ricci tensor, but the rim geometry is actually described by Riemann tensor, which has 20 components. So even if in 4 dimensions, 3+1, 3+1, which means that the Einstein equation actually algebraically so fixed for you 10 relevant components of geometry, but still there are 10 which are not fixed. And in order to fix them, you need to solve the Einstein equation, which are complicated. Nobody knows what is the general solution, of course, of Einstein equation. In order to solve this problem in 3+1 dimension, I will have really to understand what is the general solution of Einstein equation given in this particular situation. Apart from the problem that Professor Kowalski mentioned, that they might be difficult to do it for point-like sources. Okay, good. So 3+1 seems hopeless. But let us count the same thing for in 2+1. Well, in 2+1, R mu is a symmetric tensor which has 6 independent components. Of R mu. And remarkably, the Riemann tensor has also 6 independent components.
The Riemann tensor is uniquely given by Ricci.
That's true because the Weil tensor identically vanishes in 3 dimensions. Okay. What does it tell you about Einstein gravity? Well,
in 1+1, it is even better because there's only one component.
That's true.
So the scalar curvature predicts entirely.
That's true. Right. Okay. Good. So, what does it tell you? Well, it tells you that if I have a source, okay. If I have a source, then I know geometry completely, at least locally. Okay? Because knowing R mu, I know all the components of Riemann tensor, which means that locally I know all the geometry. Okay.
So you exclude gravitational waves.
There are, in 3+1 dimension, there are no gravitational waves. Newtonian interaction is absent.
Yes.
What about the constraints that the Bianchi impose on T mu? Because you cannot know T mu until you know.
Oh yeah, sure. But I'm counting the components. Of course, there are some identities that these components satisfy, right?
But these identities involve the metric.
These identities involve the metric. We know that this object, both left-hand side and right-hand side of this object satisfy some identity, which is the covariant derivative of left-hand side is 0, and this translates into nice conservation equation on the right-hand side, right?
Does it mean that if somebody gives me R mu, I'm always able to find G mu?
No, if T mu is equal to 0 into +1, there are three non-equivalent solutions, which is flat, hyperbolic, and spherical, right?
Well, no. Why? Because if you have a flat hyperbolic, you need cosmological constant, and spherical also.
But the T mu is 0.
Well, all right. If you think, okay, well, all right. But anyway, if T mu is 0 and the cosmological constant is 0 in this language, then there is a unique solution, at least locally, of course, right? We know that if there are no sources, which will be important in a moment, if I have no sources into +1 gravity, then I know that locally geometry is just Minkowski flat. That I know. Although it doesn't need to be globally this way. Okay, good. There is also one peculiar property of gravity into +1 dimensions, which is that if you take if you actually look at the action over gravity, you find immediately that the dimension of gravitation constant is actually 1.
So you have to assume in addition that Ricci scalar is 0. Then you will have, otherwise you have three different solutions.
Well, but if Ricci is 0, then the Ricci scalar is if Ricci tensor is 0, then Ricci scalar is 0.
I don't want Ricci being 0. I want that Einstein equations are satisfied. Einstein equations have.
But still, if I contract this equation with G, I get the Ricci is 0, right? Okay, good. So a remarkable thing about 2 + 1 gravity is the gravitational constant has a dimension 1 over mass. Okay. Which is, so I can identify gravitational constant with the inverse of the Planck mass. On the other hand, the Planck length, which is square root of h bar g, again, I think it's, h by g in this here, is, so my point is that the Planck mass in 2 + 1 dimension, which is one of the characteristics of quantum gravity in 3 + 1, is actually a pure classical concept. It does not need h bar to be defined. However, L Planck, which is the Planck length, needs h bar to be defined, which means that quantum gravity in 2 + 1 dimension is not completely trivial. Okay. Even in spite of the fact that the Planck mass, so the energy scale associated with gravity, is actually a completely classical object here, which also has remarkable consequences, as we will see in a moment. Okay, good. So let me return to my original question, to this one, and let's try to figure out how to solve it. So suppose I have a point, so let me try first to understand what does it mean that I have a particle, what is geometry of a space-time in which I have a point particle with a mass. For simplicity, the same discussion can be made for the particle with spin. It's a little bit more complicated. But in the case of pure mass, the situation is really simple, and it was actually this solution was actually derived by Staruszkiewicz in the early 60s, and then the understanding of it was developed in the 80s by Deser, Marjakiv, and Hoft. Okay, so what is going to be geometry? So think, I know that everywhere where there is no mass, there are no material sources, the geometry is flat. So there must be a flat space everywhere, except that there is a single point. Suppose I can always use the homomorphism invariance of the theory just to put the particle at rest at some given time. Okay. So I consider space. The space is flat. There is, at the origin, there is a delta-like singularity of the curvature tensor, right, by Einstein equation, because T mu nu is proportional to delta and m. This can be associated with curvature tensor. So the curvature tensor is everywhere 0, except that there is a singularity at some point. So what is the natural way of thinking about this geometry? Well, the natural way of thinking about the geometry is to think about the cone. Imagine a cone like this. What I can say about geometry of the cone? Well, first of all, I can say that everywhere, any local, on any local open subset of the cone, geometry is just flat if this subset does not contain this tip of the cone. And you can easily find, so if you consider this geometry of the cone, for example, if you take a metric of the cone, then and calculate the Riemann tensor, you find immediately that the Riemann tensor is 0 everywhere, but here in which it has a delta-like singularity. Okay? So this is the metric geometry associated with a point particle at rest. We know also that this angle alpha is related to the mass of the particle. Alpha is essentially mgm, or m over Planck mass. Okay? All right. So this is how the situation looks like. I have but look, this is only the first step in our problem, because I would like to understand what is the back reaction of the geometry on the particle. What I did here, I just assumed that there is a particle, and I found the geometry associated with it. So I want to do better than that. And to do better than that, I really need to switch to, oh, by the way, how much time do I have?
1 hour.
Which means that I still have 25 minutes. 25 minutes, all right. I started 5 past 10, so I have half an hour, and given the 5-minute long discussion about the cheesecakes, I may even have 35, right? Okay, good. So,
What is space like in this cone?
sorry? This is space. This is just space. So this is for constant time. T
Multiplied.
constant. So the total geometry of space-time is the cone times r. I assume that the particle is at rest, right? I can always make the particle at rest, and then the splitting of is pretty natural. Okay. In order to answer the question I'm posing here, I really need to turn to a slightly different formulation of GR in 2+1 dimensions, and it was a remarkable discovery of Witten, which was actually also noticed. That this fact was also noticed by Paul Townsend and somebody whose name I can never be able to remember. But before this famous paper of Witten about 3D gravity, there was a paper by Townsend and somebody else who actually noticed the same thing. Well, namely, Witten noticed that gravity in 2+1 dimension can be described as a very particular kind of a gauge theory. Can be described by Chern-Simon theory of a connection or gauge field valid in Poincaré group. Okay. I don't know if you how much should I tell about gauge theories?
But three-dimensional Poincaré.
Three-dimensional Poincaré, of course. Okay. 2+1 dimension. In 3 dimensions, right. 2 plus 1 gravity can be described by the Chern-Simons theory of the Poincaré group. And also, if you switch, if you have cosmological constant, there is a similar statement, and instead of Poincaré group, I have either de Sitter group or anti-de Sitter group. What does it mean? Well, that means, well, I'm not going to tell you much about the Lagrangian. I will just tell you about the basic building block, which is actually remarkably natural and simple. And for some strange way, it actually doesn't really work in 4 dimensions also, this construction. So let me, well, you know, gravity is about motions, right? Arbitrary motions. The Poincaré group is a flat space.
That gravity is not the theory about arbitrary motion. I have to object. I may sit quietly if you are talking about the 2 plus 1 gravity, to understand where it's applicable, but the gravity is clearly not arbitrary motion. Free is not arbitrary. I'm sorry.
All right, so let me put it differently. Okay, fine, perfect, good. So, if I have asymptotically flat space, the asymptotic symmetry group, at least in spatial infinity, is a Poincaré group. Okay? That's true, right? Well, hold on, I'm talking just in general. The only thing I'm now talking about the structure. Sorry. I'm giving you one particular argument, and then I will let you contemplate why there is something funny about it. Okay, so let's put it differently. I would think, from my perspective, it's quite natural to think that gravity is a gauge theory of the Poincaré group. The Poincaré group is a group of motion of flat Minkowski space, and a natural generalization, like the generalization that is actually made in gauge theories, is to consider the local theory. The theory with the same local symmetry. So I upgrade global symmetry to local symmetry. It seems the Poincaré symmetry is the symmetry of flat space-time. I would upgrade it to gauge theory, and then I will actually, I'm almost getting gravity. But funny enough, in 4 dimensions, in order to find what is the dynamical structure of the theory, to define the Lagrangian, and somehow we need to break down the local Poincaré symmetry down to local Lorentz. So in a sense, gravity, if you think about gravity as a gauge theory, that's a gauge theory of local Lorentz symmetry, not a local Poincaré symmetry. Having said that, so let's consider 2 plus 1 dimensions. Or perhaps before I do it, so let me Poincaré algebra in 2 plus 1. It concerns, okay, in 2 plus 1 dimensions, if I have 2 plus 1 dimensional space-time, there are obviously 3 translations that I denote by PA. They commute. Okay. And also there are 3 Lorentz symmetries, well actually 2 boosts and one rotation, right? Because the boosts there is 1 boost for any space dimension, and there is one rotation because the space is essentially a 2-dimensional manifold. So let me denote it by J. They satisfy SO to 1 algebra, so epsilon A, B, C, J, C. And we know that translation behave like vectors with respect to Lorentz transformation, which gives you something like this. That's it. Oh, the this epsilon, but I raised index here. So epsilon has indices always down. And I assume that epsilon 0, 1, 2 is 1. Okay?
So one of J's is the angular momentum.
The one of J is rotation. So usually J0 is associated rotation. And Ji are boosts.
Boost.
Yeah. Boost generators. So that's how it is. Okay. Now, if I want to gauge this theory, this.
So who are some brackets?
No, these are just generators. So this is just the algebra. So that's the algebra.
Then dimensions are not correct.
Well, whatever. Why?
Not whatever, but you need H bar.
No, why? That's just
J has a dimension.
These are just matrices. These are just matrices. Generators. I'm talking about here.
Nothing to do with angular momentum.
Well, indeed, it has to do with angular momentum. Well, not quantum mechanical angular momentum, but if you make this representation on a vector space, you will see that these guys just act as rotation on the vector space.
But they cannot act on wave functions, right? If they are matrices. The spectrum of boosts is.
You can always look. You can always rescale the generator by H bar. So this is not really, if there is a number or not, it's not really a problem. Of course, there is a representation of this algebra, which is the representation of Poincare algebra acting on a, I don't know, field of quantum mechanical wave functions, right? You can think about the representation of this algebra. Anyway, so assume that I form a gauge field which is, by the way, a gauge field that you can actually form in 3+1 dimension as well. As essentially, I think it was Professor Trautmann who actually constructed this theory first, just doing this, working a little bit in the language of form or translating somehow the work of Cartan. This was basically the first step. In 4 dimensions, but this is in 3 actually. Okay, but of course you can do analogous construction in 3 dimensions.
You take a particular representation of J, right, to define AB.
Yes. In some particular fundamental representation. Well, it doesn't really matter because it translates only when you. Sorry.
The fundamental representation. Which representation?
Well, you don't really need to do that because you can always, if you change the representation.
If I want to visualize AB, I would like to see how it
as a matrix, okay. Basically, okay. The easiest representation you can think of is actually the 3-dimensional representation, 4-dimensional representation, in which the Lorentz sector sits here. So this matrix J's are 3 by 3 here, and P's are here, and the P is defined in such a way that this is 1 here for the algebra. There is 1 here in appropriate place. Everywhere else there is 0. And the Lorentz part actually
is a 4 by 4 matrix.
For example, you don't really need for the construction. You don't really need the explicit, the explicit matrix representation. But well, you can do it.
And omega of x is an arbitrary function.
There are 2 gauge fields here. The first gauge field, which is which I would call a triad here, or which is essentially, a 3-dimensional field associated, which is in the language of Trautmann, this is a soldering form. Okay, and this is the Lorentz connection.
However, everything happens in a fiber, in a really abstract fiber bundle whose base is this space-time manifold, and fibers are just Poincare group.
Exactly. Yeah.
Supposed to be simple.
It was supposed to be simple. Yeah. So in the language.
There's a definition of the function, matrix function.
So this is the definition of the Lie algebra valued 1 form. Okay. Which is gauge field. Gauge field in any gauge theory is a Lie algebra valued gauge 1 form, right?
At the moment, I don't see any relation of this with gravity.
Okay, so I know.
So AB is a there are three matrices here.
Mm-hmm.
They are functions of space-time.
That's right. So there are three. This guy, well, actually, I'm surprised you don't see any connection with gravity, because this is essentially the definition of gravitational of the. This is the definition that's the starting point for the Descartes formulation of gravity. For example, the covariant derivative of this guy with respect to this connection. So you can actually calculate. Okay, so what you can do? This is the gauge field. I can find what is the curvature associated with the gauge field.
Does not have any index.
Sorry.
No A here.
Okay. F mu.
There is no A.
There is no A.
No.
That's true. So if I can find the Young-Mills curvature of this, I can decompose it into the generators.
Please write the definition of F mu in terms of omega.
Yes, just in a moment.
Just a connection in an abstract fiber band.
Not abstract, I want to
Okay, F mu
the
nu.
matrices.
F mu nu A is equal to d mu A nu A.
Yeah, A doesn't have an index.
Okay, so let me A mu. Let me TA is actually the set of all generators. Okay, so I can decompose this guy into, which is exactly this thing, right? And F mu nu is equal to, it depends on convention. Okay, this is just a standard Young-Mills field strength. This I can calculate. This I can always calculate just by using this algebra. Okay, good. So this is, and actually what is interesting is this, because if you check, when you do the calculation, you find that this curvature strength actually decomposes into Lorentz part of the curvature, which is essentially a Riemann tensor, and a torsion. And actually the same thing happens in 3+1 dimension. What are the equations? So the vacuum equations following from the Chern-Simons theory is the theory which essentially has as its equation, field equation, the equation that this generalized curvature is 0, which means that the Riemann part of the curvature is 0, so Riemann tensor is 0, and the torsion is 0. This actually is not present, this condition is not present in the case of metric gravity, right? Because in metric gravity you assume essentially the torsion is 0. But here it's clearly it's clearly visible. So I have these two equations, which essentially is telling me that that curvature and torsion are 0. Okay, at least in the case in which there are no sources. Good.
These are not the standard equations that one would get for Young-Mills.
These are not the standard equation that you get from Young-Mills, because the action here, as defined by Witten, is not the action of Young-Mills theory, but the Chern-Simons theory. So the action is something like what it is. I think this is a trace, if I remember correctly. Wait, hold on. What it is? Oh yeah, okay. It's epsilon mu nu rho, a mu f nu rho, plus or minus. There is a factor of 1/3 epsilon mu nu rho, a mu a nu a rho. So this is something like that. And the trace, of course, with respect to the gauge indices. This is the action for Chern-Simons theory, and then if you work it out, you will see that the equations, the field equation from this following from this action, actually are telling you that f itself is 0. It's compared to Young-Mills action, which is actually a trace of f mu nu, right? Which is completely different action. This action is topological because it's essentially telling you that the geometry, at least in the flat case, the geometry is just flat. Okay, so there are no local degrees of freedom.
Why in this context this action is interesting?
Oh, because it's exactly the Einstein action. That means that if I...
What do you mean exactly?
This is exactly the Einstein action because...
Without sources.
Without sources, of course, because if I associate... This is a kind of a triad, so it's associated with the metric G mu nu is equal eta AB. This is essentially what the relation between triad and the metric is. Well, it's any dimension, right? Then if you express this action in terms of G, solve for omega, the equation for omega, which is essentially, so you assume that torsion vanishes. If you assume that torsion vanishes, omega can be expressed in terms of E uniquely. You plug everything there, and you express this action as an action in terms of G, and you find that this is nothing but the Einstein action.
The curvature scalar.
Exactly. So that's why it's, so this is a different form of the action. There are subtleties, of course, and the basic subtlety is that in the metric formulation of Einstein theory, we assume that metric is non-degenerate. This is a basic assumption. And in this gauge formulation of the theory, there is no reason to assume that E is not singular or simply non-zero, which would translate in a singular metric. Which means that the phase space, if I think about the phase space of the theory, differs, or the configuration space of these two theories, they differ. On the other hand, there is no way I can I know which one of them is the right one.
The idea how to generalize it to 4 dimensions, because this is based on the fact that that epsilon has 3 indices.
Yes, I have the idea how to generalize it to 4 dimensions. I do. The problem is that, as I told you at some point, this generalization requires breaking from Poincare symmetry down to Lorentz. If you look at this action is manifestly invariant under the whole local Poincare symmetry.
I love breaking Poincare symmetry to Lorentz, but you are unable to produce epsilon with 3 indices.
That's true, but then you play in the following way. You define a new object, this one, which are called B mu nu. Mu nu rho a rho, and then you get an action which is actually B mu nu F mu nu, where B is an independent field, which is so-called, this is Chern-Simon topological theory, but there is another theory which is called BF theory, which is, right? And then BF formulation can be actually generalized to 4 dimensions.
Yeah, I agree, but it's completely different.
Well, in 3 dimensions, BF theory and Chern-Simon theory are completely equivalent.
Yes, because you have only 1 index.
That's exactly right. But you asked me if there is a way you can generalize it to 4, and you cannot generalize it in this form, but you can generalize the equivalent form of the action. Okay. So may I, because I have even given everything, I have only 10 minutes to give you my basic point, because I wanted to go to deformation. And so let me actually tell you how would I get this deformation, and tell you about this little nice computation that you can do. But in order to do this, I need first a general solution of vacuum Einstein equation. General solution of vacuum Einstein equation. Here it exists, locally, of course. The Einstein equation are essentially telling you that curvature is 0 and Riemann that the torsion is 0 and Riemann curvature is 0, or Lorentz curvature is 0. And this translates by this equation in the frame that I put into some little frame to the statement that F, which means the field strength, is actually 0. If a field strength is 0, that means that the connection, right? I mean, from basic gauge theory, if curvature is 0 or field strength is 0 for Young-Mills, then the connection has this pure gauge form, right? Good. Which means that the general solution hold on, let me check my conventions. Just in a moment. It has this.
So what is F?
F, okay. F is an element. F is an element of the Lie algebra generated by P's. The Lie subalgebra of this Poincaré algebra generated by P's that you can actually identify with R3. So F is FAPA, but you can always associate it, just say that this is just a set of 3 real numbers.
It's a function of X.
Of course, both of them. Of course.
Yeah, of course.
Everything is here. A function of 3 space-time of 3 space-time coordinates, and G is an element of SO21 group generated by Lorentz transformations. So essentially, G is a general Lorentz transformation, and E is essentially associated with a kind of F. You may think of F as kind of translation because momenta basically can be associated with translation. So this is some kind of translation. F tells you that there is a little translation, and then it's getting rotated by Lorentz transformations. This is a general solution. This is a general solution of the Einstein equations. So let me now return to this.
And what about those cones?
No, there is just vacuum. I'm in a vacuum now.
This is also vacuum
Except for one point. But this solution, what I'm saying, is that on any simply connected region, this is the general solution of Einstein equation in this region.
That it is simply connected. Yeah.
Well, this is just, if I have a vacuum, no matter, then of course I have a full space which is simply connected, it's fine. But now I would like to use this knowledge in order to actually characterize this kind of a solution. And in order to do that, I will do a set of little tricks, and let me actually show these tricks as pictures. First of all, let me actually
remove the upper part of this cone.
Exactly. So in the first step, I actually removing the upper part of the cone. But this region is still not simply connected. So I actually make another step in which let me draw it. I make a cut. In which way? In this way, I'm obtaining from this. I did some surgery to this space-time, and then to this space, and then I get a space which is simply connected. Now, let me introduce coordinates. This is coordinate phi. This is coordinate r. Suppose that this is r equals 0 here. I can always do that. And now, what should I assume in order to make this guy, this geometry of this object, identical with this geometry? Well, two things I need to do. First of all, I need to impose the continuity condition on this cut, right? Because the connection must be, or the gauge physical fields might be continuous here. So I know that, for example, E A mu defined at some r say this is, let this be pi, and this will be minus pi at some t and at pi, must be equal to EA mu R t minus pi. This is one thing. The second thing, and the same for omega, the second thing I need to do is actually to make this line, this upper boundary, look like a line, to make it one-dimensional. How to do it? Well, I do it in the following way. I just assume the circumference or the length of this segment must be equal to 0. Okay? If it's equal to 0, then of course it's essentially identical to the line, to the point. How do I impose this? Well, I impose this condition by assuming that the phi component of the tetrad at r equals 0, t and phi is just equal to 0. Well, it follows from this condition the g phi component of the metric, so the metric in phi direction is just 0. Okay, so I make use of the fact that since this is Chern-Simons theory, I can have a singular configuration, which is.
If you would shift this by a constant.
If I would shift in phi, what do you mean by shift?
Yeah, I mean you have a cone which is cut. I can now, instead of gluing periodically like you do what was done in 19th century. You shift these cuts vertically by a constant and then paste them.
Well, this is.
Yeah,
so if you
all this story is known since 19th century. It's called elasticity theory. It's 2 plus 1 dimension. It's elasticity theory, and all this story is known. All this it has never been. It was even written in such a fancy way by some people, and
well,
that condition, for example, is what is called the Volterra condition.
Well, this is a trivial condition. I don't doubt.
Well, it's trivial because you do it, but I mean you can do it much more general.
You can do it much more general, but
then it's also done, and there are these Russian people like Volovik and the others who make a living by writing that elasticity theory is a 2 plus 1 dimension. I mean, I don't understand most of these words. I somehow know what is the elasticity theory by accident, because I brought my hands. I don't know what is the elasticity theory. And I mean, this F, for example, this equation up there, is also known in elasticity theory.
I don't doubt that this is known.
Lepschter composition.
That's no.
F is probably the strain function or stress. There are these language they use there. So
I'm not.
Three-dimensional elasticity is laboratory science, which you can test the signature.
First of all, the signature is different, and secondly, the dynamics of the theory is completely different.
The mathematics is essentially identical.
Yeah, right. But then of course, if I may, then of course you can say like Einstein's like Feynman. At some point in Feynman lectures of physics, he says that the same equation has the same solutions, which is of course right. But that doesn't mean that all of physics or the part of physics which are described by the same equation are trivial. So if you have one solution of some equation, then all physics of everything else described by the same equation is trivial. It's completely non-trivial because physics is not a.
Why I mentioned elasticity theory is that I somehow think that this is unjust to associate all the achievements of science to.
I am not.
There were other people who had done. No.
As a matter of fact, it has nothing to do with Witten, but. All right. Okay. Anyway.
The conclusion is that there is some mathematical connections.
There is, obviously.
Yeah.
Obviously.
You get this way all the solutions, yeah.
Obviously there is, and there is a okay, but there is a lots of connection because it's connected to pure mass. It collects. Well, three-dimensional physics is very rich, so methods developed in one part can be used in another part, and vice versa. Anyway, so let me go back to the point. May I still absorb you for 10 minutes?
I think that 10 is too much because we have another seminar.
You have another seminar. Okay, good. So, so let me just tell you. Let me just tell you what the point of all this construction is. Actually, so let's try to figure out how can I solve this equation. Well, the first equation, which is the equation which tells you that this object must be continuous across the cut, tell me that the element G that characterize the connection and the triad at any r and any t with phi equal pi must be equal u to minus 1 times g at minus pi, where u is a constant matrix, which may depend on time, but cannot depend on either r or x. Why? Sorry, no. U is just a constant matrix. Constant SO to 1 element. If you look at the equation at the bottom, it's clear that if I multiply G from the left by a constant matrix, then it goes through the derivative and cancels the same element on the right. Okay? Then F is defined, so call it at pi, is equal to u to minus 1 F minus V, where V is another constant matrix times u. Okay, so this is the general solution. Then I need to impose this condition. This condition, if you play a little bit with it, it tells you, so if I use this and use the fact that
so you get all possible solutions which contain two constant objects, V and U.
Well, this is some more than that. Because if I take this, then this essentially is telling you, this condition is telling you that d phi of a function f must be equal 0. Because if e phi is 0, then if you look at the upper definition, then f cannot depend on phi. At least at all. Sorry, at least at r equals 0. Of course, at r equals 0. Good. If f does not depend on phi and r equals 0, then f at r equals 0 might depend only on t, right? So let me define f of r equals 0, t equal x of t. Then if you look at this equation, you find it that V, which is a constant matrix, must be equal x of t minus u x of t u to minus 1. Okay. Now let me differentiate. V is this guy. This is a constant matrix.
V depends upon what?
On nothing. It's just a constant. Since V is a constant, then if I differentiate over time, I get the following equation. X of t dot of t is equal u x dot of t u to minus 1. Okay. Okay, so let me make now the whole.
So x on the left is different from x
No, it's the same.
No, X commutes with U.
That means that U,
Commutes with X. With X
the U must be, X is an element of Lie algebra, essentially, and U is an element of the group. This condition essentially is telling you that U must have a form of the group element generated by the vector in Lie algebra, which is exactly parallel to X dot. Okay? All right. Which is actually nice. And then, because I have 1 minute, so let me tell you what the rest of the story is in 1 minute. It turns out that U can be expressed, since it's a group element of SU21, can be expressed in the following form. And the fact that I use the letter P here is not an accident, because then you can show by checking particular properties that P is nothing but is nothing but the well, let me put P over kappa to make it completely.
What was that?
Sorry, not kappa, my Planck. In order to make it dimensionless, the group element is defined in this way, where this is the object PA, which M Planck in the.
But there are already 3 P's. Yeah, so P3 is
0, 1, 2.
Ah, okay.
The 0, 1, 2, and this is P3. This is a group element, and then you can show that this PA can be, well, actually are nothing but the momenta of this particular part of the particle. Which means that, in fact, what we have to do is a deformation in the following sense. Well, the determinant of this matrix must be equal 1 from definition, which translates into the following condition, namely P3 squared minus P0 squared plus P1 squared plus P2 squared is equal equal 1, which is telling you that momentum space of this particular particle is actually not flat any longer. It's not a Minkowski space, but it becomes the anti-de Sitter space. Well, this is the or de Sitter space in this particular case, which means that the momentum space is actually becoming curved, and the momenta can be associated with some coordinates on the particular group. This can be the fact that these are really the physical moment of the particle, follows from following consideration. First of all, you can actually show what is the dispersion, the mass shell relation, so relation between this momenta and the mass of the particle. And the condition is okay. The condition is that the mass shell condition, so P0 squared minus P squared, energy squared minus momentum squared, is equal to some nonlinear combination which involves the original mass of the particle, but it involves also Planck mass. And indeed, in the limit in which Planck mass going to infinity.
What is this lowercase m?
It's just the mass of the particle I started with. So it was the particle of mass m. This I can calculate actually by actually calculating the holonomy around the holonomy here of the connection, and then related to the mass of the particle. It turns out that this condition actually takes this particular form. This is the first thing. This is the first. I need to finish now. So let me tell you what's the because I didn't actually make it half through what I wanted to say, which is my fault. I'm sorry. I should have actually speed up a little bit. So what about the basic point? The basic point is that if you think about the original problem, which was what's going to happen if I want to describe a particle, including its own gravitational field, in the context of 2+1 gravity, then the answer to this question is, what I'm getting is the kind of a deformed description of the particle in which the momentum space is no longer flat, but becomes a curved manifold. You can actually, it's even more specific, it becomes a group manifold of some particular group. You can show that if the combination of momentum, instead of being just a linear combination of components, so if I want to calculate the total momentum of two particles, then the way to do it is to multiply these two group elements of these two particles. And this is the only consistent way you can define what is the total momentum of the particles. What you can also show is you can show that in this case, the coordinate in a phase space which is in natural way dual to momentum becomes non-commutative. So by introduction, by taking this gravity into account, so taking this back reaction of gravity into account, you end up with a situation in which space-time, or the dual object which is dual to momentum space, becomes non-commutative. And this all is deeply related with the program of non-commutative space-time. And it's also deeply related to the program of quantum groups as quantum symmetry, as the groups of symmetries or the object that describes symmetries of quantum space-time. And last but not least, indeed it can be shown that if you consider quantum gravity, so forget now, this is the picture with particles, but if you consider the pure quantum gravity in 2+1 dimension, and try to ask yourself the question, what are the symmetries of flat space-time in quantum gravity? It turns out that this is in fact a very specific and well-defined quantum groups instead of the Poincaré group of symmetries of classical spacetime. I'm afraid I didn't have time really to talk more about it, but this is, I think this, well, it's far after the end of my time. I'm sorry for extending this.